Good morning. Today I'm going to present our project, PCA-based compression for cardiac MRI images. This work explores how principal component analysis can simplify large medical imaging datasets while preserving critical anatomical features of the heart. Cardiovascular diseases, or CVDs, are the leading cause of death worldwide, which makes early diagnosis incredibly important. Cardiac MRI is a key tool for this. It offers a non-invasive way to examine heart anatomy, focusing on structures like the left ventricle, which is LV, and myocardium, which is called MYO. However, as the use of MRI in healthcare grows, so does the demand for medical data analysis and storage. This creates a need for efficient compression methods to manage this large data set without losing critical details. Our project investigates how PCA can help meet this challenge by compressing cardiac MRI images effectively. The goal of our project is to study PCA's effectiveness in compressing and reconstructing the cardiac MRI images. In particular, we perform experimental studies to analyze the behavior of the principal components and the quality of reconstructed images. We evaluated the quality by peak signal-to-noise ratio, or PSNR. Besides, we use Horn's parallel analysis to select the best top K components. We used the ACDC dataset, which is an open-source collection of cardiac MRIs from automated cardiac diagnosis challenge, which included 200 simulated MRI frames from 100 patients. In total of 1,902 slices, these short-axis images are perfect for studying the heart because they show a wheel-like pattern, highlighting the left ventricle, or we should call LV, bright, as you can see, is a bright circular area, and the myocardium, the darker ring around it. These structures are vital for diagnosing heart conditions, and our aim was to compress these images while keeping these details intact. The images on this slide give you a sense of the cardiac structure that we are going to focus on. Before applying PCA, we pre-process the images in 3 steps. First, we crop the region of interest. Use the segmentation labels from the ACDC dataset to focus on the LV and MYO. Next, we normalize the pixel values to a standard grayscale range of 0 to 255. Finally, we resize all images to 64 by 64 pixels, resulting in 4,096 dimensions per images. Our experiment involved applying PCAs to all 1,902 preprocessed images, and we used Horn's parallel analysis to select the number of components, ensuring we retained only the most significant ones. Then we reconstruct the images using the truncated matrices to evaluate how well the compressed versions preserve the original details. Let us explore why PCA is a good fit for this task. So, why did we choose PCA? PCA projects high-dimensional data onto fewer dimensions by identifying the most important patterns, such as the LV shape, while discarding less relevant details. Nowadays, due to the increasing demand for MRI and medical data analysis, we need to store lots of images. We can select components based on the explained variance ratios, and by sharing similar structures between different patients, which ensure we keep key patterns easier and remove noise. A common issue in MRI image. We can save memory by using an efficient image compression method. The algorithm is actually simple. We center the image data, then perform singular value decomposition. Select the number of components by choosing from the one with highest eigenvalue. Compress the data, and then reconstruct the image. This makes PCA an efficient tool for medical imaging application like ours. To further automate component selection, we use Horn parallel analysis. First, we compute the mean pixel value and the covariance matrix of the centered data, then find the eigenvalue and eigenvectors, which indicate the variation each component captures. We then permute the data multiple times to create random datasets and calculate their eigenvalues. We set a threshold at the top 5 percentile of these permitted eigenvalues, keeping only components whose actual eigenvalues exceeded this threshold. This ensures we retain meaningful patterns, not noise. Finally, we projected the data onto the selected component when we construct the images, balancing compression and quality. This slide shows the experimental variance ratio plot, which quantifies the proportion of variance captured by each principal component. The curve demonstrates a characteristic steep decline followed by a plateau, indicating that the first few components account for the majority of biological variation in our data. This analysis guided our selections of components needed to preserve important structures, specifically the left ventricle and myocardium, while achieving efficient dimensionality reduction. For this slide, we visualize the first 6 principal components. The first component separates the foreground, and the second component separates the background. The fifth component captures the structure of the LV and RV, while the sixth component emphasizes the MYO. This observation shows that PCA can extract meaningful geometric features of the heart, which is critical for compression because it means we are preserving the most important structural details while reducing the data size. To measure reconstruction quality, we use PSNR between the original resighted images and the recovered images. This table shows PSNR values for choosing different components to reconstruct the images. With 100 components, the mean PSNR for all 1,902 images was 73.55, improving to 84.59 with 7 components. Here we randomly choose 3 images. The first images, the 160 images, and 350 images. The trend is actually similar. More components yield better quality. We also conducted a horsepower analysis for these 3 selected images, set the p-value at 0.95, and the results are approximately 600. Starting from this slide, we will visualize some of the images to verify the results by our eyes. The top one is the original resighted image. The leftmost one on the second row is the reconstructed images based on the top 100 components. The one next to it is the compressed image based on the top 400 components. The rightmost one is the reconstruction based on the components of Horn parallel analysis. From this example, we can see that the reconstructed image with 100 components is a little bit blurry, which shows the noise is larger when only using 100 components. However, for this example, we could actually still see the shape of different parts, except for the details, including the holes, which is actually the vessel scanned in LV. The smaller K components smooth the edge, then the details become blurry. Then it indicates there is a smoothing effect, especially for the outer range of the MYO. Though it is originally dark, we could actually still separate them to the background from the original one. However, for the leftmost reconstructed images, we could not find the edges of the MYO. We could also see that the right ventricle, or RV, even leaks out to match the little bright part in K when K is equals to 100. Though their shape and figures are almost unchanged, although the edges are slightly blurred. There is another example. As shown in the images with 100 components, we can see that the edges and the intensity of the images are blurred, and the shape of LV is not clear. However, the images become much clearer for K equals to 400 and by Horn's analysis, which choose 589 components. For the third example, what's different about this image is that it is in low light condition, so there are more white dots when the component is smaller, especially in the darker position of the original preprocessed image. We can see that the shape for the PCA compression is actually similar to the original preprocessed image. However, for these examples, the main difference, as we mentioned, is the white dots after the reconstruction. It appeared even after construction with 100 components, 400 components, and even also in the Horn analysis. Still, the amount of white dots becomes smaller and smaller after the number of components increased. It is generated by the short noise caused by the loss of information. Compare the original and the reconstructed image. We can see that the important LV and MYO view-like patterns are retained by PCA. Their shape and figures are almost unchanged. Almost the edges are slightly blurred. Medical analysis that based on the volume of LV and MYO is still effective. However, there are still some limitations. First, noise and artifacts are produced in the reconstructed images, especially in those dimmer regions. Second, for small K, the reconstructed images have been smoothed, losing the sharpness of edges. Third, resolution loss, as we have to resize our images to one standard size, which could lose the original resolution details. PCA-based compression preserves the critical cardiac structural features. It demonstrated viability for medical image compression. For future work, we can combine with wavelet transforms for resolution preservation or implementing adaptive component selections of per image. To conclude, PCA effectively compresses cardiac MRI images while preserving key features, and home parallel analysis automates the process. This is our project. Thank you for listening.